Hello, everyone. I'm Dave Voutila. I'm here from Neo4j to talk to you today about graph data science. I'm a field sales or solutions engineer, depending on the day of the week and when you ask me what my title is. I've got a blog as well that I write up a couple different posts about graph data science topics using Neo4j. You can also reach me via email. I'll have that back at the end of the slides as well, in case you want to reach out with any questions. And if you're curious, you can reach out and connect to me on LinkedIn as well. I'm from Neo4j, as I mentioned. We are the largest dedicated investment in graphs and graph technology, adopted by the majority of the Fortune 50, used by a handful of customers. You can see here on the right-hand side. I'm going to be focusing specifically on what Neo4j can do for you around making better predictions with graphs using the data you already have. That's the key point here. So what is graph data science? Before I jump into the demo, just want to give you a little bit of background. There's really kind of three different topics when we say graph data science, and it's really the intersection of all of them that we're providing in our platform. There's graph algorithms, which we've pre-canned into a library. We'll be using those in the demo. There's graph visualization around things like Neo4j Bloom to help analysts and non-scientists explore data visually, and as well as the ability to run graph queries using the Cypher query language. The key point here today is that the relationships that we're going to use and leverage with graph data science already exist in your data, and we're just going to help surface that and analyze it. There's a variety of use cases. These shouldn't be that new to you. If you're in data science or artificial intelligence, machine learning, etc., these are basically the cornerstone of where those things get applied. It's everything from fraud detection to cybersecurity, really making better, more accurate, valuable predictions with data. Some good case studies online, and you can talk to us at our booth about these as well if you're interested. AstraZeneca and Meredith are using the Graph Data Science Library to help really tap into and leverage the data they have and really improve upon their graph investments already. But enough talk. Let's get a look at the framework. So I'll be showing you a couple different pieces here, and really the highlights are focused on showing you how the Graph Data Science Library is practical. So it's got all the tools and pieces that you need to be productive day one, and it's put together in a way that's understandable and easy to use. It's also integrated deeply with Neo4j and the Neo4j database, so you don't have to really worry about having to fit anything together. It's already baked in. And there's also Neo4j Bloom. We won't be able to get to it in the demo today, but stop by the booth and we can give you a demo of that specifically. It's a nice visual exploration tool that lets you look at the results of your graph data science output. And when I say graph data science library, it's really a collection of graph algorithms we've already productized. And the key thing is it's all built to be run in a nice flexible analytic workspace. We'll be going through this in the demo and showing you how you create a mutable in-memory graph from your Neo4j database you've already built. Some of the algorithms we've got baked into the product. We'll be using centrality, similarity, and community detection today, a couple different versions. We've also just released node embeddings. So if you want to better integrate graphs into your existing ML pipelines, node embeddings are a great way to take the structure of a graph, pull it out of the database, and stick it into a variety of different algorithms you might be already running. But enough talk, let's get into the demo. So I'll be using Neo4j Desktop today, which you can get for free at neo4j.com/download. So if you'd like, you can also build out your own version of the demo if you reach out and get the data set. Our data set in question is a variety of business-to-business retail purchases. So if we take a look at the schema for this, you can see we've got a graph connecting customers to items via transactions. So it's business-to-business, B2B. Think of this as retail stores that might be ordering from a middleman, some sort of distributor that will restock their shelves. So our customers in this case could be the mom and pop shops, brick and mortars, etc. They order from us batches of items and transactions. Those items roll up into different categories via our product catalog, for instance. Customers might come from a variety of different countries. Now, we've got a couple different questions of the data we're going to ask. Today, I'm going to walk you through different ways you can do customer segmentation. We're going to explore two different hypotheses around this. We're also going to do some very quick item recommendations. So what maybe should be recommended as a co-purchase? So if somebody's trying to restock one item, should we be offering them another item as well? Or should we be offering them something in place if, for instance, we're out of stock? What's really the best item that we should be putting in front of our customers? And then lastly, we'll get into more some business level questions and analyzing these segments and recommendations we create. So let's go ahead and test these hypotheses. So in our graph, we had the idea of a product catalog and categories. So one hypothesis we might have is maybe we can segment our customers based off of the types of products they buy. So if we've already done an exhaustive work building this beautiful catalog and grouping our items thematically, maybe it's as simple as saying, okay, these customers tend to order this type of product versus this type, and we can kind of group them that way for marketing purposes or whatever. We'll use the graph data science library to create what's called a graph projection. So we're going to project from our underlying database into memory, into the in-memory graph. We're going to give that projection a name. We'll call it customer similarity graph category. And we're going to use Neo4j's Cypher query language to do this. So we're going to target the nodes we want to project. So in this case, we're going to look for all our customers in our categories, which if I go back to our schema for a second, you'll see blue node here on the left, orange node here on the far right. Now, the challenge is with any sort of graph data science algorithm, they tend to want either monopartite or bipartite graphs. Now, this particular graph we've got isn't that at all. So how do we get there? How do we connect customers to categories? Well, if you've used Neo4j before, you know Cypher, you can really write a pattern that'll express the traversal through there from customers to transactions, through the items that are grouped in that transaction, ultimately to their categories. So while I'm going to explain this while this runs, so this is our relationship projection. So this is going to logically define the edges in our in-memory graph. So we're simplifying, we're distilling down our database into this bipartite customer category in-memory graph. We're putting these edges in place, and this is where we're going to run our algorithms. So if we take a look down below, the results of this projection, you can see the number of relationships we're pulling into memory is actually much, much higher than what's materialized in the database. If we take a look here in the upper left, you can see across all the relationships throughout the database, we've only got about 1 million. In this case, we projected, if my glasses are good, 31, just about 32 million edges into memory. So there's a nice efficient way to take your Neo4j database, be able to project this into memory, and most importantly, run our algorithms. The first thing we can do is try to find ways things are similar. So in this case, we can use node similarity. We can create a new relationship between the items in the graph. So based off of the customers and the categories, we can see our customer is really similar based off of common categories. So the mutate version is going to just work on this in-memory projection. It's not writing anything back to disk. It's not putting anything back in the database. So this is extremely efficient. So the algorithm runs on the in-memory projection. We're mutating it in place, and you'll see we're writing another 43,000 relationships into the in-memory projection already. Top K, similarity cutoff. These are parameters related to node similarity. So if you're more curious about how the algorithm works, definitely check out our documentation. We've done a great job explaining what each algorithm is, what all the parameters are, and providing links to all the academic literature that we use as the basis for understanding the state of the art of the algorithm. So we just created all these similarity edges, but we still haven't clustered anything. So let's run community detection. So we'll use Louvain modularity. Just like before, it's baked into the graph data science library. So we're going to use a stored procedure call. You'll notice instead of mutate, we're going to use stream. So this is going to allow us to pull the results out of this projection as we run the algorithm and just return the results directly into, in this case, Neo4j browser. We're going to target the new similar relationship that we created in that projection. So it doesn't exist in our database yet, but it is in this projection. And we're going to use that score from node similarity as the weights, because Louvain supports weights and finding ways to build these communities. Out pops the node ID, its community assignment. We're going to then group those up and count them so we can get an eyeball of how this looks. And when we run it, we can see it's garbage. So you'll see a community ID of 1. It's 4,300 in size. Now, we only have, a couple thousand customers in this database. Probably not the most efficient way to segment them. We've got a segment that is gigantic, Second level one is 71, and then everything else, the long tail, is just individuals. And in that case, there's only a couple individuals too. So our hypothesis that we could use our product catalog to segment them isn't really valid. Maybe it's our catalog's fault, who knows, but the data doesn't lie. So what can we do instead? Well, instead of that, maybe we could try maybe not looking at the catalog, but the items themselves. So first, nice thing to do is you always clean up after yourself. We have this in-memory projection. We can drop it. That frees up that memory for us to run some more algorithms and create more projections. So let's do another load. Instead of doing customers to categories, let's do just customers and items. Now, the beauty of this is if we go back to our schema, you'll see we've already got a direct relationship between customers and items. Maybe we did that ourselves. Maybe someone did it for us. Maybe that's just how it shook out. I'm not sure, but we can leverage it. The beauty of that is we can use our native loader. And the Graph Data Science native loader can talk directly to the database, bypass the Cypher runtime, bypass all the query processing, and just read directly out of memory. So we can create that projection again. And this time, instead of using Cypher statements, we just say, target these labels. So give us customers and items, and it give us the bot relationship as a way to connect them. When you run this, you'll see it's a lot faster. You probably even think nothing happens because it only took a millisecond, and it literally just took longer to render the results than it did to run, basically. We've still got a tremendous amount of relationships. In this case, it's a little less, but let's take a look at the quality here. So we'll run node similarity again. You'll see nothing really changes. That's the beauty here. We still give it the name of the projection. All the inputs can stay the same. Still using the same outputs in this case of mutating, creating a similar relationship, using score. Everything we just learned in part one, totally applicable to part two. While that runs, I'll queue up our Louvain run. Same thing as before. We're going to use the similar relationship type that popped out of our node similarity run down below. We're going to look at these communities. And now, if we take a look at the results, they look a lot better. So we've still got a bit of a long tail. We've got some folks. You know, it could be indicative of maybe we just have some customers that just haven't bought a lot yet. Usually you'll have, you know, a couple of your heavy hitters that do most of your revenue. But the buckets here, if you look at the community sizes, it looks a lot more, you know, appealing from a segmentation perspective. We still don't know why they're segmented like this. This is still very opaque to us, but this looks like something we can run with. So that's great. We've used Stream to eyeball it. Now, the key thing here is that we like these results. Let's materialize them. So the first thing we could do is use the mutate version. So it'll change the in-memory graph projection again, creating a Louvain community property on the nodes. But we can also write back to the database. So in this case, we're going to use this approach where we mutate the projection, and then we use write node properties to pull out of the projection and stick the results in the database. So we're going to target just this updated property. So when I run this, these are going to run back to back. They're going to mutate our underlying database. And now we've materialized the output of our community detection into the Neo4j database underneath the covers. So now if somebody else wanted to run Cypher queries, you want to drop Bloom on top and visualize what this looks like, you're good to go. So we just did our segmentation. Let's try running with these segments. Now, we still don't fully understand what's going on with them, but maybe we'll learn something along the way. Let's try to do a little bit of a simplistic recommendation approach here, something that's sort of akin to collaborative filtering. So what we can do is going to be a little verbose. And I've got to run it a couple of times, so I'm going to walk you through the first time, and we're just going to blast through a couple of runs of this. The first thing we're going to use is item similarity. So we're going to do a little bit of cleanup in case there's anything lingering in our database. You'll notice we're doing another graph projection, and we're using a Cypher projection. So in this case, we're looking at transactions and items, but then specifically, we're going to filter down the way we connect these things based off of looking at the new Louvain community properties. We're going to target specific communities, in this case, one community at a time, find all the transactions those customers made in that community, and then tie those to the items that they pertain to. That projection is then going to be held in memory, where we're going to run node similarity. Once again, we're going to create a new relationship type in that projection. We're going to call it similar underscore and then the community ID. So it's going to be 4 digits, I believe. We're going to put the weight on there as a score property. And then we're going to write that back to the underlying database as well. So we're going to use that same pattern as before, mutate, write. And then we're going to clean up after ourselves and just drop this projection. I'm going to run this. While this runs, I'm going to queue up the next batch here, and let's walk through how the centrality is going to work. So similar, we're going to do a little bit of cleanup, make sure we don't have anything held up in memory. I'm going to create a similar projection, but this time we're going to look at items to items. So filter down the items that our customers bought based off of customers being in the target community. And then we're going to look at, is there a way to go from one item to another via a relationship to that particular customer? So in this case, through bots. So like if I bought one item, what other items did I buy? We're going to directly connect those together in our projection. Let me just double check that that's done. Yep. I'm going to run this while I'm talking about it just to help speed things up. And we're going to use the closeness algorithm. And this is a way of measuring centrality. And it's going to write, in this case, directly to the underlying database. And we're going to create a new property called closeness centrality community underscore community ID. A little verbose and wordy, really testing my ability to speak clearly on this recording. We're also going to use PageRank. So closeness and PageRank are going to work somewhat similarly, but quite different in their applications. So closeness is going to really tell us how well, basically we're going to use these two things. PageRank is going to tell us how influential something is, and closeness is going to tell us if it really appears with a lot of items as well. So we'll see this a little bit later on. I'll have a little bit better explanation about the difference between when we see a high closeness and low PageRank. And it should be a little bit apparent once we see the data. Then we're going to clean up and drop the graph. So this one takes a little bit longer to run. So while that's running, I'm going to queue up another batch. So we just did it for one community, 2929. Let's queue it up for, let's see, we want item similarity for, let's do 5214, according to my little note there. It's ready to run. Closeness is almost done. It's doing the write. It's running PageRank. And that's done. So we're going to run the similarity for this particular community. While that runs, I'll queue up 5214. For centrality, we'll run this. You'll notice I'm using some niceties of Neo4j browser. So I'm using these named parameters. So I'm able to use the cipher templates and interweave parameter references. So I'm able to templatize the cipher. So this is a good way in which if you wanted to really batch this, let's say we wanted to run this for our top 20 communities, and we don't want to sit here and type in 4 digits every time, hit run, et cetera, because clearly this is not the most exciting part of the demo. You could use this parameter-based approach, create a list, iterate over these lists, run these in batches. And then you can just come back when it's done, after you grab a cup of coffee. Now, if we take a look at our schema, we've got new relationships in our database. So we materialize these to the underlying database. Similar 299, similar 5214. If we take a look at what these look like, you can see these items. So there's a similarity relationship, for instance, between, let me scroll down. Should clear out this query box. We've got on this particular item, vintage cream cat food container. So there's some measure of similarity. In this case, it looks pretty low because it's 0.13 to this airline bag. At some point, it might have been purchased with it or purchased by the same customer, maybe not necessarily at the same time. And there's a variety of other properties related to the output. So we've got it in our database. Now let's take a look at some of the questions we can answer now using Cypher. So the key part is we've generated our recommendations using graph data science. And now we can lean on the power of the Cypher query language to do ad hoc exploration of the output that's in the database. So let's say maybe we want to look at the differences between two communities. And we now want to understand, instead of just having these be opaque, really what's different between them? Are there items that are kind of grouped together, similar in one, that are not similar in another? So we can say, find us all these items that might be related through the similar relationship from that 2929 Louvain community, but do not have a relationship from the other community, and then make sure that the scores are within some sort of acceptable range. So we've got a variety of products here. You can scroll down. There's a lot of things related to chives or rosemary, chives and thyme. So in this case, these items are all grouped together. It looks like these tend to be food related. So in community 2929, they tend to be purchased together. So this is probably something more around food or cooking, household items. Although I'm not sure what bicycle puncture repair kits would be doing in places selling a lot of herbs, but I don't know, maybe people bike to that store. So let's flip it around now and say the other direction. So what's similar and grouped together in 5214 that's not in 2929? We run this query, get a bit more, this bicycle stuff. This is in England, and maybe they love their bicycles. But we see paper cups and plates. We do see some herbs and things like that. A variety of other things involving felt sheep, Christmas musical tree, Christmas trees, pink hearts, things of that nature. Quite a little bit different. We could repeat this for different communities and try to get a better understanding of maybe how these customers are similar. But we could also look at maybe what's different between what's important in one community versus another. So let's look at their page ranks as well. So not just what's similar, but also let's look at the key items, the most influential ones, specifically the ones that are very different between these communities. Dolly Girl, Children's Bowl, Children's Cup. So a lot of kids items. So in one community, they have very high page ranks. You can see on the far right. And in the other one, not so much. I mean, there's quite the difference between them. So one of them seems to be very much heavily skewed towards maybe children's items, children's gifts, things like that. Children's cutlery, apparently, circus parade. Not quite sure what that would be. But maybe we want to understand more about the dynamics of these customers and really their businesses and how they stock items and what they sell. If we take a look at items that have, for instance, high centrality, but a low page rank, that means that they're not as influential. They're not really like a key item, a cornerstone to a purchase, but they're included in a lot of purchases. They appear quite a bit, co-appear, co-occur. These could be things that are maybe at the point of sale. Could be, like the candy bar that sits there, or the really trashy magazine that somebody buys and throws in with their groceries. If we take a look here, so this is high centrality, low page rank. We've got maybe a lot of the cheaper items, a paperweight, for instance. I mean, who's going out and buying a bunch of things with a paperweight? Maybe a single bath sponge, stuff that we probably don't want to be buying in groups necessarily. Could be cheap items. But maybe let's look at the inverse. Maybe what are the items that tend to be kind of bought in groups that don't tend to just kind of co-occur with almost everything, that aren't common? So let's flip it around a little bit. Take a look. So high page rank, low closeness. Got some stickers. Those could probably go either way. But if we look, this tends to be, once again, a bit more of either holiday items, kids items, or really some party items. If we scroll down a bit, wedding card. You know, typically if you're getting a card for someone, you're probably also getting a gift. So it's usually not just kind of thrown in with things potentially. And some owls, hanging owls, Ollie beak. Interesting. And clearly this is from the UK. So this tells us a little bit about maybe how the behavior is different between our customers in terms of what they order, and maybe how we should be targeting, you know, folks in one community versus another, which offers or items or things we push to them. At this point, we had a couple different options. We could then take this output in our database. We could drop Neo4j Bloom on top and visualize everything. We could also use Neo4j browser as well and navigate the results. So if we go back to our presentation here, to recap, we just showed you a bit of a retail demo using the Graph Data Science Library to go through the graph projections, run algorithms, materialize those to the database, and then start to use the Cypher query language to really inspect and analyze and also validate our hypotheses. And we learned a little bit about the weird buying habits of these UK businesses along the way. If you're curious about some more use cases, I've got some material online on my blog related to fraud detection with graph data science, specifically around first-party fraud in a mobile money network, as well as a use case around how to use the graph embeddings. So taking a co-occurrence graph, generating a structural embedding of who co-occurs or appears with somebody else in a story, and then taking that output and running it through scikit-learn to do clustering outside of Neo4j, which, as I just showed you, you can always do it within Neo4j using graph data science, but this is another way you could integrate with other tools and platforms. If you'd like to learn more about graph databases in general, everybody who's attended the demo today is able to get a free copy of Graph Databases for Dummies. Just stop by our virtual booth and we can hook you up. We've got a great talk from one of our customers, Bank of Montreal. They're going to be talking about knowledge graphs in the financial institutions and how they use Neo4j in order to drive insight and increase business value. We've also got a cybersecurity demo we've recorded. It does touch upon a little bit of graph data science. In there, we're using, I believe, some PageRank and some other algorithms to help understand how to find kind of critical points in a network and where you're most exposed from a security perspective. And as I mentioned, stop by our booth. If you've got any questions about the demo, about topics, about graph data science, we've got graph data experts there to talk to you. You can also pick up that copy of your book for free and register to win some cool prizes. And lastly, I'd like to thank you for attending today. If you've got any questions, you want to reach out and get the data set, some of the queries, feel free to email me, dave.voutila@neo4j.com. Thanks.